like didn't plug in my phone. So like by this morning it was dead. Oh man. What did you say? No, I felt like shit because I was late for work. Oh, that's so great. No. I felt like shit. Because I got up and had to get rushed and like didn't just like shower and make breakfast or anything like that. I just had to like run straight to work. So I can't handle it.
Okay, I'd like to mention that we grade request you today.
Well, I asked him.
Where do we turn them in?
You can send them to me. Send them to me. So we grade request. Okay. Okay, today we're going to talk about Fourier Transform shift and modulation properties. That is 8.1 of the textbook. Okay, so modulation, at least we're going to learn about amplitude modulation. And this is how your AM radio works. Okay, there is another kind of modulation called frequency modulation, which is kind of slightly more complicated. But we're not learning today. FM radio. Okay, so let's learn about Fourier transform shift, something that you already know. That if you have Fourier transform given by this formula over here, and what is the Fourier transform of a delayed quantity? Okay, so it's very simple. You just plug it in, and you should have this as your answer. And now you can lump that exponential term together with your Fourier transform and rewrite it as a product of two terms. F of omega. Okay, so you conclude that f of t minus t naught Fourier transform to e to the minus j omega t naught f of omega. Okay, a time delay is equivalent to a phase shift. You add a phase to the signal when you do a time delay. So what this means is that if you have f of t that looks something like this, say an arbitrary signal that looks something like that, and then f of t minus t naught will look something like that. This was the origin. So at t equals t naught is where the origin should be now. So your time signal should look something like this. T equals t naught. Okay, so a time delay, or t minus t naught, is equivalent to shifting the signal to the right. Can everybody see this? If this plot looks like that, this plot should look something like that. Because when t equals t naught is where this thing peaks at 1, for instance. Okay, this is one value. This is also having the value of 1. Okay, but this property can also go in the reverse direction. That is, if I were to have f of omega being equal to minus infinity to infinity dt f of t e to the minus j omega t, that is the definition of a Fourier transform, then if I were to add the phase to this signal, say j omega naught of t, okay, if I were to add the phase to this signal, what does the Fourier transform to? Okay, so you can see that if I were to do that, then I can rewrite this signal and rewrite the Fourier transform of this thing. Let's say this is g of t. If we can write the Fourier transform of g of t as f of t e to the j omega naught t e to the minus j omega t. Okay, this would be g of omega. And if you look at this properly, it is equal to minus infinity to infinity dt f of t e to the minus j omega minus omega naught t. Okay? And then if you compare the first formula with the last formula, this is just f of omega minus omega naught. Agree? So if you were to add the phase to a time signal and find its Fourier transform will be frequency shifted. Okay, very much like this property over here. This is the duality property of Fourier transform. And this can be used to shift the spectrum of a signal. Say if you don't like a low frequency signal, and if f of omega, let me draw it up here. If f of omega is low frequency, okay, it has a lot of low frequency spectrum, adding a phase to this function will change this to something that looks like that. And then this is omega equal to omega naught. This is omega equal to 0. So you shift the spectrum to the right-hand side. And it's shifted to the right-hand side because you do only one thing. You only multiply by one phase vector. If you're clever, and if you want to maintain this thing to be real value, you will do something like this. You will say that I want f of t to be multiplied by e to the j omega naught t plus e to the minus j omega naught t. What is this equal to? That is equal to something from a trigonometric identity that we have memorized, 2 times the cosine of things. So this entire thing now is real value. If I call this g of t, it is entirely real value. And then if I take its Fourier transform, if I make use of this property, it will have 2 terms. The first term will be frequency shifted to the right. The second term will be frequency shifted to the left. Okay? And if I plot this spectrum now, you will have something that looks like this, as well as the part that looks like that. Okay. Is this clear? And does f of omega have to be a real number? does this have to be a real number? If this is real number, if this is real value, does this have to be real value? What do you know about this property? Fourier, right? What do you think this should be? Is it real value or not?
It is real value.
No, the answer is incorrect. Let me ask another person. What property does f of omega have?
It's imaginary.
Not imaginary. If this is real value, f of omega has to have certain property.
Oh yeah.
It can be a complex number, but this complex number has a special property. This complex. Okay, very good. Xiaofeng Li, right? Not Xiaofeng. It's not exactly an odd property, but a conjugation property. Okay, if this is equal to that, it will ensure that that f of t is always real value. Okay? So when I plot things like this, I actually cannot plot this thing to be real value. I actually have to plot its magnitude. So otherwise I have to plot the phase alongside with it. Then if I plot its magnitude, it will look something like that. Because this thing, most of the time, 99% of the time, is a complex number with an amplitude and phase. So you can only plot its amplitude. So its amplitude will look something like this. Okay? So this is a great thing. It means that if I have a voice signal, and if you're a very good signal, and if you're a soprano, your voice signal cannot exceed how many hertz? What? 20 kilohertz, right? 20 kilohertz is the highest frequency that human ears can hear. Soprano probably sings below that, because we can hear much higher than what a soprano can sing. Okay?
Soprano like the mafia?
Mafia. I don't know about the mafia. So if you have a voice signal,
Whoa, sorry.
okay, so your bandwidth is probably something like this. This is probably 20 kilohertz times 2 pi minus 20 kilohertz times 2 pi. Okay, your voice signal is something like that. And it's pretty low frequency in terms of electrical signals. And what is the signal that you have inside your computer, your desktop PC? You know what frequency does that oscillate at? 3 gigahertz, right? 3 gigahertz. 3 gigahertz is 3 times 10 to the 9 hertz. Okay? So compared to what you have inside your computer, 3 times 10 to the 9 hertz. Okay, so this kind of hertz is actually very small. And AM580, I forgot. I think that's 580 kilohertz. Okay, if you like WILL, right? I always say it's about AM580. I think it's 580 kilohertz. Okay, so all the radio signals are much higher. Anything that you need to transmit over airspace has to be at a higher frequency. Do you know why? Yes?
There's more things to interrupt.
If you try to transmit a very low frequency signal over air, it's very difficult. It's very difficult because it's a basic physical property of electromagnetic radiation. Electromagnetic radiation is due to a dipole. You make an antenna. A simple-minded picture of an antenna is that you hook this antenna to a signal. Okay, then you will have current flowing in that antenna, something like this. Building up charges here and then depleting charges over here. And this is a simple picture of an antenna. And this antenna generates electromagnetic fields at radius, like that. And so so in order to get this antenna to radiate well, these currents have to go back and forth at a very high rate, high frequency. So if it goes at 20 kilohertz, it's too slow. Okay, it's too slow. Just imagine the speed of light. 20 kilohertz is very slow, and then this thing actually radiates poorly. So in order to get this antenna to radiate well, you have to have this current going back and forth at a much higher frequency. So that's why you have the AM580 kilohertz. That is about how many times? Hundreds of times, tens of hundreds of times higher than your voice signal. And then you have FM1, FM101, or something like that. Those are megahertz signals. FM signals are much higher. And then you have microwave that goes at gigahertz. Okay, and then you have all these electromagnetic radiations that are at a much higher frequency. It's because at a higher frequency you can get these things, the electrons, to go back and forth very rapidly, and these antennas become much better radiator. So it's almost impossible to send signal over the air at this kind of frequency. However, if you were to modulate it, as you can see from this picture, if you will just go through this intermodulation procedure, okay, this is like 2ft times cosine of omega naught t. If you multiply your voice signal with a cosinusoidal signal, the spectrum changes. It goes to a much higher frequency. And that frequency is centered around omega naught. And this is usually called a carrier. Carrier frequency. Okay? And because you can modulate it so that the voice signal has a much higher frequency, you can send it over the air much more easily with a small piece of metal. Okay, you have a cell phone, and then everybody carries a cell phone, including myself, and there's a small antenna in there. And if it has a 20 kilohertz signal trying to accept the antenna cannot radiate. This thing probably operates on the order of maybe sub-gigahertz, okay, very high frequency. So the antenna can be very small, and it's very small, and then it can radiate really well. Okay, so there's the idea of modulation. And after modulation, you shift the spectrum, okay? And so the simple procedure of a modulation circuit is just this one over here. You have a voice signal coming in. You have a multiplier. You multiply by the carrier frequency. This is called omega c in the textbook. And out comes a modulated signal, which is cos of omega c t. So if I were to plot this signal, is kind of hard to plot, but if this signal is something like this, the voice signal is at very low frequency. The voice signal might look something like that, and then multiply that with cosine of omega naught t, or omega ct. It might look something like this. Okay, so there's an envelope. Okay, so if you look at this signal, it has a much higher frequency component, and you can send that signal over air. Okay, in terms of bandwidth, what happens then is that if I were to draw the bandwidth of the modulated signal, the output of which I call G of omega over the other side, instead of having this over here, you would have the signal over here plus its image. Okay? So this is omega c, this is omega c, minus omega c, and I call this G of t. Is equal to that. Why do I always have an image term over here? Why is this term not 0? Why is it that whenever I have something over here, I have to have something over here? Comes from that pair. How did that pair come about? You know? Why do I always have them occurring in pair in the Fourier space? In the time domain, I don't have to, right?
Fourier
Fourier coefficients come in pair. Why do they always come in pair? Shofeng, what do you think the reason is? What? No, it's this property that I just brought to your attention just now. For every positive omega, there's a negative omega that's the conjugate of the positive omega. If you have a real value signal, for every positive frequency, there's always a negative frequency. Okay? So if I draw something here, I have to draw its complex conjugate over here. Otherwise, these two together will not give me real value. It's together with these two that I get a real value signal. Do you understand this, or do you catch this? Georgie, do you catch this? Okay, good. You're a smart guy. Okay.
He says he's going to get 100 lexes and...
Okay. So the rule of thumb that the textbook gave is that the size of the antenna that you have, if I call this L is much, much larger than lambda over 4. Lambda over 4 is the wavelength of the electromagnetic signal. And what is the wavelength given by for an electromagnetic wave? Lambda equals to frequency times something. Lambda equals to velocity. What is the formula for lambda?
Lambda equals C times 11.
In terms of C,
Times 11.
times what? The lower the frequency, the larger the wavelength. So would the F go into numerator or denominator? Denominator. Okay, so you learn this from your physics. What is that? 212 or 211 or? So lambda is C over F. So if you have very high frequency signal, C is equal to what? C equals to, what is that?
2.998 times 10
2998 10 to the 8, right? Something like this. Very high.
Per second.
What?
Per second.
Yes, per second. Yeah. So it's an extremely high speed signal. I mean, extremely high velocity wave. And that carries your mobile phone signal and all your signals around the globe. And it can go around the globe 7 times in 1 second. Okay, so it's extremely fast. And because of that, then with frequencies on the order of gigahertz, then you can get this to be something that can fit into your pocket size. Okay? So you can make antennas that are small enough to fit into your pocket. Okay? So example, let's do example 8.3 is a little bit strange, but let's do it anyhow. So it has a f of t, and then if you modulate it by this strange function, n is equal to 1 to infinity, 1 over n cosine of n omega naught t. Okay. How does the spectrum of M look like? How does the spectrum of M look like? That's what it asks you to find. Okay. So probably a no-brainer for most of you, right? Yeah. If you know that if you multiply by omega 1 cosine, you get 1 spectrum like this. If you multiply by different cosines of different frequencies, you get a whole bunch of spectrum that are shifted with different numbers. Okay, so if f of t looks something like this, the first term will give you that, the second term will give you something that is slightly diminished in amplitude and maybe shifted over something like this with amplitude that is smaller, and then the next one will give you something maybe over here with smaller amplitude and so on. Okay, and you just compute more and more of that. So it's not very difficult. Okay, you just apply this formula over and over again. Okay, let's talk about demodulation. You have modulated a signal. You have converted the low frequency signal into a high frequency signal so that you can put it through an antenna, get it to radiate. You have to receive this signal, and after you have received this signal, how do you convert it into something that you can hear? Because you cannot hear anything that is beyond 20 kilohertz. This signal could be in the order of gigahertz because of the carrier that it has. This could have been shifted way into the gigahertz range so that you can use a small pocket cell phone to talk to each other. Okay? So how do we demodulate the signal so that we can get this signal back? So you have this signal that has been sent to you. Okay? So next topic should be, how do we demodulate the signal that we have received? So this is section 8.2, coherent demodulation of AM signal. AM means amplitude modulated signal, because I just make it like this. This is AM. I just modulate the amplitude with the voice signal. Okay? So you can imagine that the signal leaves your antenna. Sometimes the symbol for an antenna is just that. Okay? The signal gets pumped into your antenna, and then it leaves it, and then it goes through this thing, and then after a while it gets received by another thing, another antenna over here. And then this propagation channel can be thought of as a channel that the electromagnetic signal propagates from antenna A to antenna B. And effectively, what it does is to give rise to a time delay. Okay? If you have somebody talk to you from Chicago, send you a signal, the signal that you receive over here in the Boeing campaign is not exactly that from Chicago, but time delayed by a very little bit. Right? Very little bit, because velocity of light is so fast. It goes around the globe 7 times in 1 second. So it's maybe just delayed by a fraction of a second. But sometimes you might need to send this signal to a satellite and let it bounce back to Earth. Then you might have some sizable delay, but still very small, fraction of a second. Okay. To model the time delay, okay, we model the transfer function, or the frequency response of the function to be equal to just a constant times e to the j omega t naught. That is what would cause a time delay. Because if input is f of t, okay, output is maybe g of t over here, okay, then you can see that g of omega is hc of omega times f of omega, and it's just f of omega times a constant times the phase shift. Okay, so g of t is just equal to a constant times f of t minus t naught. That's what the propagation channel go to your signal. And K can be a kind of attenuation. You can think of K as being a kind of attenuation. Because if you send a signal to your cell phone they don't send it directly from Chicago to here though, they usually go to base stations. Your cell phone signal hops. Okay, it hops to a base station, and then from a base station it hops to another base station, and maybe sometimes even hop to a satellite and then get sent from a satellite down to another base station in the Urbana-Champaign area, and then it gets sent to you. Okay, so the Earth surface is covered by cells, and each cell has a base station. That's why you call your phone a cell phone, because the cell phone actually belongs to a cell of this communication network that we have designed for you. So, but roughly, it's just a time delay. Okay, the signal goes from Chicago to you, it goes up to the satellite and comes back. It's just being delayed by a fraction of a second. Okay, so we can model that delay. But the cell phone signal also has to propagate through long distance. And when say if the signal propagates from your cell phone to the base station, if you start with amplitude of 1 in terms of its amplitude, by the time it gets to the base station, it might be a lot smaller. Because the wave that leaves your cell phone is a spherical wave. Have you heard of spherical wave? That if you have a point source, the wave leaves the cell phone like a spherical wave. So this is 1 over r decay. What? The power goes as 1 over r squared, but the strength of the signal goes as 1 over r. Okay, the electric field goes as 1 over r. So you have this kind of attenuation going from the cell phone to the base station, and then the base station might have to talk to the satellite. So you need some power amplifier in between to boost the signal. Okay, at your base station and the satellite and all kinds of things. And all the attenuation that you experience as a cell phone goes from Chicago to here. If your mom calls you up, your dad calls you up, the amplitude might not be the same. But finally, in your cell phone, there's also a power amplifier in there. And then boost the signal back to something like that. And let's say that the difference in the amplitude is modeled by this K. And this is what this K means. Okay? So, how do we convert that signal back to something that is audible, that you can hear with your human ear? Okay, so the received signal would be something that is K f t minus t naught cosine of omega c t minus t naught, because it's just time delayed version. I modulated a time delay, I multiply by an attenuation. That is what you have at the receiver. Okay? That's what I have at the receiver. But this signal is not audible to you. Why is that so? You cannot hear it. It's too high frequency unless you are a bat. Bat. High frequency, right? So, but even bats cannot hear such high frequencies. Okay? No living creatures can hear such frequencies. So what we need to do is to do some kind of a demodulation. Okay? So if we multiply this signal with another sinusoidal signal that is exactly delayed by the same time, then what I have is K f t minus t naught cosine square omega c t minus t naught. Okay? So what is the Fourier transform of f of omega? Then how you do this is to try to express this into products of exponentials. If you write that as products of exponentials, then you realize that, or you can do it a number of ways using trigonometric identities. And if you use trigonometric identity, what is cosine square of omega t? You don't know how to find the Fourier transform of this, but you know some simpler form. Okay, so if I write this, this would be 2. Let me see. What is the trigonometric identity to use here?
1 minus cosine of 2 omega t.
What is that? I know that cosine square theta minus sine square theta is equal to cosine of 2 theta, right? I know this to be true. And then so it's 2 cosine square theta minus 1 is equal to cosine of 2 theta. So cosine square theta is 1 plus cosine of 2 theta over 2. Did I do it right? I think I'm okay. Okay? So you can use this trigonometric identity and write this as half plus half cosine of 2 omega c t minus t naught. This is what this is. Okay? And then I can rewrite this in terms of exponentials again. This would be e to the 2j omega c t minus t naught plus e to the minus 2j omega c t minus t naught. And I put a quarter here because the cosine contributes to another half. Okay, so now m of t is given by f of t multiplied by that 3 terms. The 3 terms here mean half plus this term plus that term over there.